Bismillahirrahmanirrahim. Welcome to Transistors and Application series. First of all, let's recap about the episode number 5. And last time we had discussed about the beta DC, what is the amplified gain, that is called the DC beta and DC alpha. These are the gains of the transistors. If we forward bias the base emitter region and reverse bias the collector base region, then our transistor is in amplifier range, and transistor can be operate as an amplifier. In today's episode, get ready for some other formulas and many formulas, I can say that, and prepare your mind. And maybe this video get some extra time. I need some extra time to explain because today's lecture is a little bit lengthy, and I will try to cover the two topics, because I received episode 6 outline, that is transistor DC model explanation plus circuit analysis. So let's start without wasting any time. First of all, first topic is the transistor transistor DC model. What is transistor DC model? DC model is nothing, just an explanation of the in easiest way, where sometimes if our like you can see that here this is the, for example, this is an NPN, and these are the biasing connections. This is an unsaturated, I'm using transistor, this is connected with positive side, and here this is connected, these are the limiting resistance, and this is connected with the with positive side here to because this is in common region here, and this is negative is connected with the N, and here this negative is also connected from this, here is another biasing source, and negative is common with this emitter region, and these terminals are known as our input region, and these are our output region. So to simplify this diagram, I'm going to draw the DC equivalent circuit. This is called DC equivalent model. Let's draw the DC equivalent model, and this is, for example, our base. This is base region. Remember, this is our base region here, and this is nothing, just limiting resistance. I'm not using this resistance right now. And this is the P region, and the P region and N region. P is connected with positive and N is connected here with negative, you can see that. And when P region is connected with positive, N is connected with negative, this is the forward bias state of the as the normal PN diode. So as this behaves like a normal diode, just the forward bias. As you know, when the forward bias, in case of the forward bias, these are the 0.7 volts drop approximately. So we are also using and all the parameters here are also same, and this looks like a normal diode, PN junction diode. This is base region and this is the emitter region. So this is the common, because so we can take also this as an input, and this is the positive, and here it is negative. So the current direction is toward from negative to positive, because we are using the not conventional, but we are using electronic flow, and this is the IB base current. And here last time we discussed that DC beta or beta DC is equals to IC divided by IB. In other words, collector current is equals to base current multiplied by the current gain. This is the current gain, and it is mentioned on our data sheets. Means to say that current gain is a dependent with the base current on base current. If our base current is increased, then it is multiplied with the gain, and our current we obtain the total I collector current. Means to say, in our amplified state, base this is an dependent region or on the I base current. So here we can represent that these are the the dependent. When we have a dependent source, we have to use like the a square, or you can say that diamond shape. diamond shape is used for to show the dependent sources, and circle symbol used for to show the independent. I use this diamond symbol here because this beta DC, this is beta, and if beta DC is, this is the DC beta, and it is the capacity that is mentioned by the manufacturer on the data sheet of the bipolar junction transistor, and this is the capacity, that the boosting capacity of the transistor, and it depends on the I base current. If I base current is forward biasing this region, and with the quantity of the current that is available, and this current after passing through will reach here, and this is after drops etc, this I base reaches when here, then it multiplies with this boosting factor, that is the PC data beta DC, and we already discussed about the beta DC in the previous episode, and then it is multiplied with this IB, and so beta DC is dependent source on IB, so that's why we use this symbol. So this is our output in the form of voltage output, or in other terms this is just an output, and this is emitter region, and this is our collector region. We obtain this type of output from the collector terminal and from emitter terminal. So this is positive and this is negative. As you can see that this is positive, and here this is negative on emitter. So let's talk start some discussion on circuit analysis. Circuit analysis. What is circuit analysis? As the name indicates, that circuit, so we have to connect our bipolar junction transistor in a circuit. Once again, I am using NPN transistor, and NPN transistor is connected in this way. This is the pattern to connect the NPN transistor. I'm grounding this, and here I'm using a limiting resistance at collector terminal, and this once again positive side is connected with this, and negative is connected with to common the both sides of the emitter, and with the negative polarity, positive negative, this is the VCC and this is VBB, and this is RB and this is RC. So here the currents are, this current flow IC here, and this current is IB, and here this current is IC. Remember that this is the emitter region, this is base region, and this is the collector region. Emitter and base, this depletion region here is called V base emitter depletion region. This depletion region that is here, it is called because this is the depletion region between the collector and base region, so we call that V collect CB voltage across CB terminals, and here the terminals are VC collector terminal and emitter terminal. So if we want to calculate across these two terminals, we have to write here voltage across CB. So remember that there are the three regions, emitter, base and collector. So there are the three currents: I collector current, I emitter current, and I base current, and there are also three voltages, that is VBE, VCB and VC. What is this? This is VCE. Also remember that these names are indicate something. Remember, first capital letter in subscript represent that this is the at base voltage. We are calculating this at base voltage. We are calculating this at collector terminal. We are collecting this at collector terminal. Means to say VB means that voltage at base with respect to emitter. Here this means that voltage at collector with respect to base, voltage at collector with respect to emitter. Second indicates with respect to. Here both at base with respect to emitter, at collector with respect to emitter, because this is grounded. So let's start our discussion, and how many 10 minutes, so I have some time here, so we can easily calculate and First of all, let's start our discussion by starting that this is VBB forward biases the base emitter region, and VCC reverse biases the base collector region, base and collector region. So when base emitter region is forward biased, let's start that when base emitter region is forward biased, this is approximately 0.7 volts drop. Understood? I know that in practical cases it can reach up to 0.9 and sometimes even up to 1 volts, but for easier understanding we will use throughout this course 0.7 volt, and it has a normal characteristic curve and all the parameters are just like the normal diode. You can see that here we use, that's why we use the normal diode here, and emitter is grounded. You can see that 0 volt meter is ground and it is called 0 volt. So applying the KVL, at which loop? KVL can be applied to any loop. So the first of all, the requirement of the KVL is a closed loop, and in a closed loop sum of the algebraic sum of all the voltages, active and passive sources, equal to 0. Here you can see that this is first of all this loop, base loop, and here VBB is providing voltage, active source is equal to, these are the passive elements, that is here this resistance is using this voltage, this resistance, and some voltage is consumed by this depletion region here across the base emitter region. So VBB is equals to voltage across RB plus some voltage here, voltage across base emitter region. VBE is equals to 0.7 volt, we know that, but VBB we also know, for example this is 5 volt and let's say this is 15 volt, we also know that what is the value of the VBB, but what is VRB? So we want to calculate the VRB, take it on one side, VBB, this VB will go to the other side, and it is no sign is changed, VBE becomes the negative quantity, and what is this VRB? It means that the voltage across the resistance R. Applying the Ohm's law here, Ohm's law, what Ohm's law state, V is equals to IR, and if we want to calculate the voltage across RB, it means the current of the at base, that is IB, and the resistance, that is RB. So we can use VRB and replace in equation number 1. The equation number 1 becomes right now equation number 1 becomes IB RB is equals to VBB. Next right hand side is same, V base emitter. So here RB is also known, and but we can now calculate the base current from this VBB minus VBE and RB. So this is a formula. Now we are almost getting too many formulas by using this. Remember that this episode is very important. Practice these and remember all these formulas. Practice makes a man perfect. So I recommend you all to practice as many times as you can. Write these formulas. Writing is very important. Sometimes you can think that you learn, but after writing you can understand how much you can learn, how much you learn something, memorized or not, anything. Anyway, now we are going to apply the KVL at the emitter loop, voltage at collector with respect to this grounded emitter. Applying KVL at emitter. Here VCC is an active source and consuming is across RC number 1 and across this whole bipolar junction transistor. In other words, across emitter and collector region. We don't know how much it is consumed because these are the two depletion region. We just know about this depletion region and we don't know about the collector and base region because this is for reverse bias and we are not sure about this. So we just write collector and emitter. Voltage across collector emitter plus voltage across RC. Voltage across RC can be calculated again by Ohm's law. Voltage across RC is equals to IC RC, just like this. So here current is IC and resistance is RC. So this equation becomes VCE plus IC RC. So this is the another equation we can calculate. Remember, these are all formulas. You have to memorize these formulas because we will use these formulas. We need these formulas in calculation. So we are not going to drive again and again these formulas. You have to memorize these formulas. Now what this equation here, if VCC is known, and if we want to, here we want to calculate VRC, what is the voltage across C and E, voltage across C and E. So here voltage at point C with respect to emitter is equals to here VCC. This, we take this ICRC on the other side and it becomes negative ICRC. So RC is also known, resistance value here. But what is IC? How we can calculate the IC? Remember this formula, beta DC is equals to IC I divided by IB. IC can be now calculated by IC is equals to this, will go to the other side and it is multiplied with beta DC, and beta DC is known in the on a data sheet, and IB is calculated earlier, as you know. So we can calculate the IC. So at the end we now want to calculate this quantity. If we want to calculate the voltage across collector base junction, voltage across the CB, we have to calculate VCE. CE means to say voltage at collector. This is collector and emitter. Overall, these are the 2 points. Voltage at collector and emitter is equals to this and this. This is the total voltage across the collector and emitter, and it is divided into base emitter plus base collector. Voltage at base emitter plus voltage at base collector, collector base. So if we want to calculate V at CB, this is the we want to calculate is equals to VCE minus, this will go to the other side and the sign is changed and it becomes VBE. This is another formula, and in the next episode we will try to use these episode. We will try to use the concepts of these episodes, and these all formulas we will use to further clear these concepts with the help of an example. So stay tuned, watch, learn, grow. See you next time.